Okay. So today we'll be discussing last couple continuous distributions, in particular the normal distribution. If you've ever taken a statistics class before, hopefully normal distribution will be at least somewhat familiar. But it's sufficiently important that it's worth reviewing. We'll also quickly cover a couple other continuous distributions that are useful in some circumstances. So the normal distribution was first introduced by, I don't know how to pronounce French names, as some approximation to binomial. It was later studied by Laplace and Gauss, who noticed that it's an interesting distribution because basically if you average just about anything, it becomes normal once you average enough of these things. This is known as the central limit theorem. We'll discuss it in more detail later. For the time being, we'll just define the distribution. Sample space, it's a continuous distribution with that can take any possible outcome in the real line. The PDF, we've discussed it briefly in the past, and you've probably seen it before at any rate. It's 1 over square root of 2 pi sigma times e to the minus y minus mu squared over 2 sigma squared. Y, once again, can take on any value between minus infinity and infinity. And the case where mu equals 0 and sigma squared equals 1 is referred to as the standard normal distribution. Was useful in the past largely because you can, as I'll show here in a second, you can standardize any normal distribution to have a standard normal distribution. And in the days before we had computers, this meant that you could calculate the CDF of the normal distribution using only one table rather than about 50 million different tables. Now it's probably a lot less critical given that we could use our SAS to calculate these things, but whatever. As there's no closed form for the CDF in general, this notation capital Phi is often used for the CDF of the standard normal distribution. A lot of statistics textbooks have tables of its values. Like I said, nowadays it's usually easier just to use R. But to calculate it, generally speaking, you'll need to use either some sort of statistical software package or some sort of table, because there's no simple way to calculate it. Usually you need to use some sort of Taylor expansion or numeric integration or something, or stuff that you really do not want to try to do by hand. Moments of the normal distribution, you can calculate reasonably easily that its expected value is mu, its variance is sigma squared, which is precisely why it was parameterized this way. If you wanted, just as I showed, I think, a couple lectures back, you can calculate its higher order central moments as well. It ends up being this expression that you can see here. And so, in particular, that gives us that the skewness of the normal distribution is 0 and the kurtosis is 3 times sigma to the 4th power. Not something that I've ever used routinely, but just in case you ever need it for whatever reason. And as I mentioned earlier, and as you've probably seen already, the normal distribution has this nice property that you can convert any normal distribution to a standard normal distribution by subtracting the mean and then dividing by the standard deviation. This works because the normal distribution is part of a family of distribution known as location scale families. We'll discuss this in more detail later on today. Likewise, given a standard normal distribution, you can convert it to a normal distribution with arbitrary mean and variance by adding mu and multiplying by sigma. And the easiest way to prove this result is using the moment generating function. You can also use the transformation of variables formulas that I discussed a week or two ago, but that gets a little bit messier. And in order for it to be a well-defined density function, it needs to integrate to 1. And you can, obviously it does, or a lot of modern statistics wouldn't work, but the question of why does it integrate to 1, and proving this result and actually calculating this integral turns out to be a bit more painful than you would expect. That the trick for doing this, and particularly if you're enrolled in 690, this type of normal integral is one of the things on the list of stuff they want you to understand. So if you're planning on taking 760 in the future, pay attention to this, even though it's a little bit convoluted. Say you want to prove that this thing integrates to 1, how would you do that? Well, let's call this integral I. So then we can calculate I squared by multiplying this integral by itself, but doing the integration once with respect to x and once with respect to y. What's the point of that? Well, we can write that as a double integral as follows, where we integrate from minus infinity to infinity with respect to both x and y of e to the minus x squared plus y squared over 2 dx dy. So what's the point of doing that? Well, if you have better memory than I do of elementary calculus, you might remember that you can do a transformation of variables to make these types of integrals easier. In particular, when you have this type of two-dimensional integral, you can convert it to polar coordinates. And that is, let x equals r cosine of theta and y equals r sine of theta. And since we're integrating over the entire space of R2, that's equivalent to letting theta go from 0 to 2 pi and the radius going from 0 to infinity. If you don't remember polar coordinates, maybe I should have included a brief review here, but the basic idea is that rather than even have a piece of chalk so that I can very quick review of polar coordinates that I probably should have put in the slides for the benefit of the people watching this on YouTube, but oh well. Say you have this point right here and you want to describe its location. Under standard Cartesian coordinate system, you would give the x-coordinate of that point and the y-coordinate of that point. Under polar coordinates, you note that it's that rather than giving x and y, an equivalent way to do it is to give the distance from that point to the origin, which we call r, and the angle that you have to turn in order to go from the origin to that point, which we call theta. So the idea here is, and if you remember from trigonometry, which I know probably goes further back than calculus for a lot of you, that given theta and r, if you want to calculate x and y, then if you just remember the formula, the cosine by definition is that adjacent over hypotenuse. So to get this x-coordinate here, you would multiply the hypotenuse times the cosine of this angle, in other words, r cosine theta. Similarly, to get y, it would be r sine of theta. So when you convert this into polar coordinates, you let x equal to r times the cosine of theta, y equal r times the sine of theta, and rather than integrating from minus infinity to infinity in the x and y's, you let r go from 0 to infinity. R can't be negative, so y the lower limit 0, and theta goes all the way around the unit circle. So in other words, from 0 to 2 pi would be the limits of integration in polar coordinates. And if you have an extraordinarily good memory, I wouldn't have remembered this if it hadn't been in my notes, you might remember that when you do this type of two-dimensional transformation, change variables for multiple integral, you need to compute this Jacobian thing, which involves taking a bunch of partial derivatives, putting it in matrix form, and then taking the determinant of that. So you take the partial derivative of x with respect to r, the partial derivative of y with respect to r, and partial derivative of x with respect to theta, the partial derivative of y with respect to theta, and end up with a matrix that looks like this. If you can't remember any of this, I apologize. It's grading the midterm. I know it sounds like a fair number of people are rusty on just what the heck is a partial derivative is, but if you don't remember any of this, you can just take my word for it, although, as I said, if you plan to take 760 in the future, you might want to review elementary calculus if you don't remember how to do this, because it's one of the things they want you to know how to do, and that is basically how to mess around with normal integrals. But you take these partial derivatives, put it in this matrix format, if you recall, to calculate a determinant. It's that times that minus that times that, where you multiply the diagonal entries by one another and then subtract. You get r cosine squared of theta plus r sine squared of theta. And again, if you remember from trig class, the sine squared of theta plus cosine squared of theta is 1. You end up with just r. So I apologize if this is causing trauma from not being able to remember calculus. But what this means is the integral can now be written as integral as r goes from 0 to infinity and theta goes from 0 to 2 pi of e to the minus r squared over 2 times r over 2 pi, which now r times e to the minus r squared over 2 has a simple antiderivative. That's just going to be minus e to the minus r squared over 2. I guess I should also know, first of all, you can pull the e to the minus r squared over 2 outside of the inner integral, or if you change the order of integration here, then you're just integrating from 0 to 2 pi of 1, which divided by 2 pi, the 2 pi cancels, you end up with just the integral from 0 to infinity of e to the minus r squared. Take the antiderivative of that, evaluate it from 0 to infinity, you end up with 1. Woohoo, it does indeed integrate to 1. So, like I said, if you're an MS student, you can probably just ignore that. I'm not going to ask you to prove this on an exam or anything, but this is on the list of things they want the PhD students to know.
So you mentioned it was okay to switch the order of integration. Is it generally okay to do that?
I think so. It's been a while since I've taken calculus as well. I think there's some conditions on this that I don't remember off the top of my head. If you want to shoot me an email, I'll look it up.
But not in any way that would impact this. Okay.
So, number of places where the normal distribution's potentially useful. The far and away the most important use, as I've alluded to earlier, is when you approximate the sampling distribution of large samples. The central limit theorem says that under very mild conditions, if you take just about any random variable with just about any distribution in the world and add them together, you end up with something that's approximately normally distributed. And I don't think we'll go into this in a huge amount of detail in this class, but it's actually quite remarkable the generality in which this result has been proved, that this works in many cases even if the variables don't have exactly the same distribution, even if they're not entirely independent, and even if a lot of the higher order moments don't exist. In general, it's a quite powerful result, and if you've had statistics in the past, you know it works remarkably quickly. That for a reasonably well-behaved distribution, you add like 5 or 10 things together, and it's already pretty close to a normal distribution. If it's a badly behaved distribution, you might need more like 20 or 30. If it's absolutely horrible with huge outliers and skewness and high variance and everything that possibly could go wrong does go wrong, then you might need like 50 or 60. It's really remarkable how well it works. And there's a number of other distributions that can be derived from the normal distribution. You've probably heard before if you've taken statistics in the past: chi-square distribution, t-distribution, f-distribution. I'm going to briefly define these here in a minute, but I'll discuss them in more detail later on. Oh, quick review of like chi-square, t, and f distributions. Chi-square distribution, if you'll remember, if z is a normal distribution with mean 0 and standard deviation 1, if you take z squared, then it has a chi-square distribution with 1 degree of freedom. And if you take a bunch of independent standard normal random variables, square them, and add them together, you can end up with a chi-square distribution with v degrees of freedom, and it has a PDF that looks like that. And v doesn't even necessarily have to be an integer, although in practice the vast majority of the time it will be. And I guess I should mention here, this gamma thing that we've defined down at the bottom, you may be wondering what the heck is that? Well, it's what's called the complete gamma function, which is defined to be this integral. The main reason we're using it here is because we just need to make sure that this PDF integrates to 1. If you actually work out this integral, it's a pain that involves integration by parts and a bunch of things. But if you work it out, you end up with something that looks like this in the numerator, so divide it by that in the denominator, and you get 1. You can show pretty easily that if a is an integer, then gamma of a is just equal to a minus 1 factorial. It gets messier. If a is not an integer, you'll probably want to use a computer in that case. Quick aside, as you'll see here in a couple of minutes, the chi-square distribution is actually a special case of the gamma distribution that gets its name, at least partially, from the gamma function. Oh, two other very important distributions in applied statistics are the t-distribution and the f-distribution. T-distribution has a PDF that looks like this. If you've taken statistics before in the past, or if you're taking 662 right now, then you probably know that if you don't know the variance of a distribution, but instead estimate the variance from the data, and then calculate the standard t-statistic where you subtract the sample mean, divide by the sample variance, that has a t-distribution. And that becomes incredibly important for many applied problems that leads to t-tests and regression inference and all kinds of other things. Likewise, if you divide a set of chi-square distributions by another set of chi-squared statistics, you end up with an F distribution that has a PDF written like this mess. luckily, we have computers to calculate that for us, so the fact that it's a huge mess isn't a major concern. It's useful for doing ANOVA tests and regression inference and things like that. And there's a number of important properties and relationships between these distributions. We'll be coming back to this and discussing these properties in more detail in a few weeks. For the time being, just noting in passing that these various distributions exist. Now, a couple other distributions that you may not have seen before unless you've taken some more advanced statistics courses, but do come in handy in some situations. One distribution is the gamma distribution, which is parameterized as follows. That I won't even bother to walk through the formula because it's kind of funky and has the gamma function once again, blah, blah, blah. Generally speaking, unless a is an integer, there's no simple form for the CDF. Moments can be calculated if you're good at integration. Usually you can do it with integration by parts and a few tricks like that. You can show that the expected value is a divided by lambda, and the variance is a divided by lambda squared. So, first thought, if you're seeing this for the first time, is why on earth would we care about that thing other than to torture students in introductory statistics classes? Well, the main advantage of the gamma distribution, at least in my experience, is that a number of other distributions are special cases of the gamma, and by figuring out some of the properties of the gamma distribution, you can more easily calculate the properties of these other distributions. That if you let a equals 1 in the gamma distribution, you'll end up with the PDF for an exponential distribution with rate parameter lambda. So one way to think of the gamma distribution is it's kind of flexible generalization of the exponential that sometimes some books will refer to like a gamma a comma lambda as a gamma distribution with shape parameter a and rate parameter lambda. And a equals 1, you get the special case of the exponential. Another special case of the gamma is that if gamma with shape parameter n over 2 and rate parameter 1/2 is just a chi-square distribution with n degrees of freedom. So once again, if you calculate if you can figure out the properties of the gamma distribution, you can use them to draw inferences about the behavior of both the exponential and chi-square distributions. And we can also see that a gamma distribution with shape parameter a is just the sum of a independent exponential distributions, assuming a is an integer. So that means that if a is an integer, the gamma distribution with shape parameter a, rate parameter lambda can be derived as the time until the 8th event in a Poisson process. Recall the Poisson distribution can be viewed as a certain process is happening at a certain rate, and you want to calculate the probability that it takes x time units until the next occurrence of the event. Well, the amount of time until you get a occurrences of the event would just be you take a Poisson random variables, add them together, because the first Poisson random variable is the time to the first event, second one would be the time to the second event, etc., etc. You add a of them together, you end up with a gamma, so you can think of the gamma as the distribution of time until the 8th event in the process. And another generalization of the exponential distribution that honestly I have not used as much in practice as the gamma is the Weibull distribution. Its sample space goes from v to infinity, where v is just some parameter. Its CDF is defined as the following: is 1 minus e to the minus y minus v over alpha to the beta. You can see this is similar to the CDF of an exponential distribution. A would correspond to the rate parameter of the exponential distribution here, but you have this parameter v, so the distribution goes from v to infinity rather than zero, and you also have this additional parameter beta, which honestly I'm not really sure what the interpretation is of that one. You can calculate the PDF, which looks like this, and the usual case is with v equals 0, meaning that it can take on values between 0 and infinity. And if you let beta equals 1, then as I said before, you end up with an exponential distribution with rate parameter 1 over alpha. Cauchy distribution, as I've alluded to earlier, it's a famous distribution for mathematical statistics because it's often useful as a counterexample, or even in applied statistics if the type of work that I do tends to be applied most of the time, and if I want to try to show that my method still gives correct results, even when you get weird data with really high variance, usually I plug Cauchy data into my method to verify that it doesn't actually blow up. And the PDF of the Cauchy distribution, the general form looks like this, where you go 1 over pi times 1 plus y minus mu squared over sigma squared. Take on any values between minus infinity to infinity. Most of the time when you use the Cauchy, you'll do it with, it isn't correct to call it mean and variance, because as I've noted earlier, the mean and variance of the Cauchy distribution technically do not exist. You could call it like central parameter, dispersion parameter, I don't know what you call it actually, but one way or another, mu equals 0, sigma equals 1 is the most common form. If it corresponds to a t-distribution with 1 degree of freedom, indicating that if you're trying to do some sort of t-test based on a sample of size 2, you're probably dead in the water because you're going to end up with something that has infinite mean and infinite variance. You can't really do any kind of inference on that. Interesting little aside, the t-distribution with 2 degrees of freedom is the only example I can think of off the top of my head that has a finite mean but infinite variance. Sometimes that's useful if you need to use a distribution that has that particular property. I mean, off the top of my head, like, I should be careful and I'm not telling you lies and check my notes before I say things like this. But if my memory is correct, which is a very big if, like the law of large numbers, which says that if you add up a bunch of things and divide by the number of things you add up, just take the sample mean, basically, that it gets closer and closer to the population mean as your sample size gets large. That only requires the existence of first moments, I think. Whereas the central limit theorem requires the existence of the first 2 moments. So if you take a t-distribution with 2 degrees of freedom and add a bunch of them together and divide by n, it will get closer and closer to 0 or whatever your population mean is. It won't be like the Cauchy distribution where you add up a bunch of things and it's not any closer to the mean than it was when you started. But it will not become normal as you add a bunch of t-distributions with 2 degrees of freedom together and then do the standard standardization, because it has infinite variance, so the central limit theorem doesn't apply. That's just interesting little aside. We'll cover this in more detail later. And the moments of the Cauchy distribution are not defined, but it is possible to calculate its quantiles. You can look forward to that on the homework. It's actually not that hard, given that the Cauchy distribution actually has a closed form CDF, which makes it relatively straightforward to calculate this. And yeah, the Cauchy distribution, the most common use of the Cauchy distribution is that you want to generate messy data that will cause your theory or methods to blow up. But that's not the only possible use for it. We'll prove later on in this class that if you take 2 standard normal random variables and then take the ratio of these 2 variables, you end up with something that has a Cauchy distribution. Which means that all kinds of bad things can happen if you try to do inference on variables that are ratios, such as famous example of this is BMI. If you take like weight divided by height, which is approximately the formula of BMI, sometimes you'll end up with a distribution that looks really weird and can cause your usual statistical methods to not perform the way they're supposed to. Another distribution that occasionally comes in handy in practice is the beta distribution, which is a distribution that goes from 0 to 1 and has a PDF that looks like this, where the denominator is what's known as a beta function that's basically defined to be a function such that the integral goes to 1. If you calculate this out, you can see that it can be written in terms of a gamma function. If A and B are integers, then you can write this in closed form. If the CDF, generally speaking, you can't calculate unless A and B are integers, but R and other statistical software will calculate this for you without much trouble. The moment, if you want to work through the math, the expected value would just be A over A plus B, and the variance will be A times B over A plus B squared times A plus B plus 1. And beta distribution's fairly flexible. You vary the parameters, you can get a wide variety of shapes. In particular, a beta 1, 1 is just a uniform distribution on 0 to 1. This is another one of those cases where if you've never seen this before, it's just going to be like, why on earth would we define something this bizarre? Well, off the top of my head, even as an applied person, I've used the beta distribution a couple times in some research problems that I've worked on. Once was a statistical genetics example that the basic idea is, this might be interesting to those of you who have taken biology before. If you haven't, it may be completely confusing. I'll try to explain it the best I can. Say you have like a human population that were once all living together and intermarrying and so forth. Then the two populations became separated, and there wasn't much contact between the two populations and started intermarrying separately. Well, over time, the frequency of certain SNPs and alleles in these two groups starts to vary due to chance, that a gene that may predispose one to a certain disease may become more common in one population, less common in other population, just due to random chance. This isn't a hypothetical concern at all. If you ever do like genetic association studies and compare, like, for example, European populations with African American populations, well, there's going to be a lot of differences just due to this genetic drift factor going on. And it turns out you can show that if you want to model the differences in the allele frequencies between the two populations over time, it follows the beta distribution with certain parameters. And you can also use this for like phylogenetic reconstruction, which is basically you have like, say, a bunch of samples from a bunch of different species and you want to figure out how they're related to one another in the evolutionary tree of life. You can model that with the beta distribution as well. I used the beta distribution recently in methodological paper that I was working on because you can show that in some cases, if you take a ratio of chi-squareds where the numerator and the denominator are not entirely independent of one another, that you can end up with something that has a beta distribution. I'll discuss this all in more detail later, but basically what we showed in this paper that I'm working on trying to get published right now is that, say, you're doing tests on a bunch of things simultaneously. Genetics is another good example. Say you're trying to find which in the set of thousands of genes is associated with a disease that you're interested in, that rather than just doing a bunch of t-tests or chi-squared tests one at a time, you can get much better power if you convert this chi-square test to a beta and then just kind of look at the distribution of the betas and look at the distribution of the test statistics compared to what you would expect under the beta distribution. I just kind of pointed at this as like evidence that even as an applied person, I still can do math sometimes, because like I recently wrote a paper that had the beta distribution and it made me feel smart. Anyway, so this is not just an entirely hypothetical thing that is used to like torture / inspire awe and first year statistics students. There actually are some problems where this distribution comes in handy. And for more details on all of this, you can read the section in Cassell and Berger if you have the textbook. So, brief discussion on larger families of distributions. This will become relevant here in a lecture or two when we discuss exponential families. But families of distributions are distributions that can be related to one another in certain ways that I'll discuss here in a moment. One of the most important examples is what's known as location and scale families, that if you have a PDF that can be written in this form, 1 over sigma times f of x minus mu over sigma, where mu is some real number and sigma is a positive number, that's known as a location scale family. And if you just let mu equal 0, then it becomes a scale family. If sigma equals 1, then it's a location family where you're either changing the scale but not the location, or you're changing the location but not the scale. And hopefully you see already a number of examples of location scale families that we've discussed already, including the normal distribution, Laplace, Cauchy, exponential distributions, all examples of location scale families. And properties of location scale families, you can say let Z be some distribution, be a random variable from some distribution that's part of the location scale family. Well, if you multiply Z by sigma and add mu, then X will have PDF f of mu comma sigma of X, where f of mu comma sigma of X is defined the way I've written it up here. And you can also show that the expected value of this new x will just be sigma times the expected value of the original variable plus mu. The variance will be sigma squared times the variance of the original variable. You've probably seen these types of formulas before in the context of the normal distribution. It turns out that the same formulas are true for any type of location scale family. And there's some broader / more complicated families of distribution known as group families that this gets into a little abstract math here, and I apologize for that, but if you say there's some class of one-to-one functions from R to R, then this class of functions is called the transformation group if two conditions are satisfied. That, number one, it's closed under composition. That is, that if you have two functions in this class, then G1 of x and G2 of x, then G1 of G2 of x, where you take the output from the first function and put it as input to the second function, that's still a function in G. And it's also closed under inversion, meaning that if a given function is in G, its inverse function is also in G. And if you have a random variable with some CDFF, the class of all random variables that can be defined by G of Z, where G comes from some transformation group, is known as a group family. And if you're like me, you look at that, you look at those equations, kind of like, meh. I'll try to give a couple examples to make it a little clearer what's going on here. This, honestly, the math of that previous definition isn't something you need to understand very well. That hopefully when I give a couple examples, see, oh, okay, I see what you mean here, and that will be all that you need for this. Like, one group family is location scale families that we just discussed. That, in this case, your function g of z is just a simple linear function where you multiply by some slope, add some y-intercept, simple linear function. And if you look at the properties on the previous page, it's very easy to show that the set of linear functions have these properties, so that's a group family. Another example of a group family is the class of all functions that are strictly increasing and whose limit is g goes to minus infinity is minus infinity, and whose limit as z goes to infinity is infinity. And any random variable with support on minus infinity to infinity, that is, that can take on any value between minus infinity to infinity, is defines a class on Z, which is just the class of all continuous random variables that have support on minus infinity to infinity and whose CDFs are continuous and strictly increasing. So, I mean, you really don't need to define all this math. It's only so that this class of distributions makes sense. You can just say that that the set of random variables that are strictly increasing, that is, there's no flat spots, it never takes on any one value with positive probability, and its support is on the entire real line, would be a class of functions. Or another example of a class of distributions, if you add the restriction that g is odd, meaning that g of minus z equals minus g of z, then you can talk about the class of all symmetric distributions, for instance. So this just gives you chances. This is just ways to define class of distributions, and later on we can show that certain classes of distributions have certain properties, which comes in handy when proving certain things. And as happens way too often, I'm done way early. Any questions about any of this? See you on Thursday then. I'll try my hardest to get the exams graded before then. Wish me luck.
So earlier you were saying like something like VMI, which is a ratio of two normally distributed variables. Sometimes you can get some distributions that just look really crazy. What happens if you get one that actually like looks normal? Can you use things that require normal distribution on it, or not?